let us first see exercise 3. Actually, we are not going to solve this. I am going to leave it to you, but we need this exercise to solve the next one. So let's see what this one is saying first. So here you see the factorization, the prime factorization of a positive integer n which is greater than 1. And the primes involved are these pi's, p1, p2 up to pr, and the exponents are respectively k1, k2 up to kr. And f is a multiplicative function which is not identically 0. Then look at this sum. Summation mu of d times f of d, where d varies over all the positive divisors of n. Then this sum is equal to this product 1 minus f of p1 times 1 minus f of p2, like that the terms go, and the final one is 1 minus f of pr. And we are going to use this result to solve this fourth one. In the fourth one also we see the prime factorization of n, where n is a positive integer greater than 1. And there are some parts, and we have to establish each part using this fact. So let us now see what the parts are. So this is part A. In part A, the summation is summation mu of d tau of d. So in place of that function f, here we have tau. And of course, d varies over all the positive divisors of n. We have to prove that this is equal to minus 1 to the power r. So in the solution, we straight away apply exercise 3. By exercise 3, this sum is this product, where in place of f, now we have tau. Now what is the tau value of a prime? Tau calculates the number of positive divisors of the argument. Here the argument is say p1. How many positive divisors does p1 have? 2 positive divisors, 1 and p1. So tau of p1 is 2. Similarly, the other tau values are also 2. So you have these 1 minus 2's multiplied together. That means you have these minus 1's multiplied together. How many of them are there? 1, 2, 3 up to r. So that's how you have minus 1 to the power r. Next we have part B, where this time in place of f you have the multiplicative function sigma. And you have to prove that this sum is equal to this product, minus 1 to the power r, like part A, but along with that you have the product of the primes involved in the prime factorization of n. So of course, again by exercise 3, this time the sum equals this product, where now we have sigma. Now what is sigma of p1? It is the sum of the positive divisors of p1. p1 has 2 positive divisors, 1 and p1. So that's why in place of this you have 1 plus p1. Similarly, here you have 1 plus p2, here you have 1 plus pr. And then after you do the calculation, this is what you get. So you get all the primes involved in the prime factorization of n along with minus signs. So you continue to get minus 1 to the power r like the previous part, but this time along with that you have the product of these primes. So that's how you get that. And then next we have part C, where we have summation mu of d divided by d here. So the function f here is not a non-multiplicative function. It's not like sigma or tau, but still it's multiplicative. What is the function actually? It's nothing but the reciprocal function. If your input is d, the output is 1 divided by d. And it is multiplicative just like tau and sigma, but in a very trivial way. Just you can show it in 2 or 3 lines that it's multiplicative. So I leave that to you. So here also we are able to apply the identity from exercise 3, and that's what we are going to do. And we have to prove that this is equal to this product, where the factors look like this, 1 minus 1 divided by pi. So the solution is nothing, it's almost like writing simply what you have been told to prove. But there is the reason, of course. What does exercise 3 give us? Exercise 3 tells us that this sum is equal to 1 minus f of p1 times 1 minus f of p2 all the way up to 1 minus f of pr, what is f of p1? Since f is the reciprocal function, f of p1 is 1 divided by p1, f of p2 is 1 divided by p2, so that's why we are getting this, that's it. And finally we have part D, where this time the function f is the identity function, f of D is just D. This, however, we already know is multiplicative, and you can see why this comes, just like that one. If f of D is equal to D, so in place of 1 minus f of p1, you will have 1 minus p1, that's it. So you just write the solution, there is nothing else to write. Let us instead see next the sixth one. So next we have number 6, where we have to find formulae for this sum and this sum in terms of the prime factorization of n. So let us see what the sums are. The first sum is having this general term, mu square of D divided by tau of D. And of course, as D varies over all the positive divisors of n. The difference in the second sum is that it's just like this one, but in place of tau, here you have sigma. So let's see how we can find expressions or formulae for these sums. Because we have to find formulae for these sums in terms of prime factorization of n, so naturally the solution starts with prime factorization. Let n be a positive integer greater than 1 having this prime factorization. Ideally you should write where these are distinct primes and where the exponents are positive integers, but I am not writing those things. So let us now see what happens. So after that we note these facts, that mu of D divided by tau of D and mu of D divided by sigma of D are both multiplicative. And if you want more elaboration on this, you go and see exercise 19 from section 6.1. Because of these facts, it follows again from exercise 3 that whatever we did in the previous exercise, that is 4, we can do the same thing here. But let us first express this sum in the form that will allow us to use exercise 3. Here the general term in the sum is mu square of D divided by tau of D. It can be written as mu of D times mu of D divided by tau of D, and this part is multiplicative. So by exercise 3, this is equal to this product. I have used the product notation because it saves space. So it's the product of terms like this, 1 minus the function f is here this. F of p1 is mu of p1 divided by tau of p, well, it's pi actually, because I am talking about the general term, and here I varies from 1 to r. Now let us simplify this product. So you can see, if you recall, mu of any prime is minus 1, and we already know that tau of pi is 2 because there are 2 positive divisors of any prime, 1 and the prime itself. So this becomes 1 plus 1 over 2 or 3 over 2. How many 3 over 2s are we seeing here in this product? R number of 3 over 2s. So it is the rth power of 3 over 2. And we can similarly work with the other sum. So this is the second sum, where now in place of tau we have sigma. So again you write this sum also like this, which allows you to use exercise 3 here. And using exercise 3, this is the product that you are getting, where now you have sigma. Now those calculations will change. So sigma of pi is the sum of the positive divisors of pi, which are 1 and pi. So you have 1 plus pi here. So minus and minus give you plus. So 1 plus 1 over 1 plus pi, or if you do the simplification, then the numerator would become 1 plus pi plus 1, that means 2 plus pi, and the denominator is 1 plus pi. And that much only you can do. It's not as nice as the previous one, but that's the best we can do.